Hey class, I'm just going to walk you through the first 3 example problems. If you need it, you can go ahead and skip ahead if you're getting the hang of it and finish the rest of these and then get started on the other practice that we have for you. First thing we want to do is determine the delta H of each reaction. So part A, I'm going to determine delta H. Let's start with the first one. Alright, delta H is going to be the products minus reactants. Remember, these are our reactants that we start with, and we go over the hill and we end up with products. So our products are over here. Looks like my value is between 40 and 60, so I'm going to call that 50. It looks like it's exactly 50. So I'm going to do products minus reactants. And my reactants look like they are, let's see, it's real close to 60. I might call it 61. If you called it 60, I wouldn't make a big deal out of it. So 50 minus 61 is going to be a negative number because 61 is bigger. And if you put it in your calculator, if you can do it in your head, either way it's okay, you end up with negative 11. And our units here are kilojoules. That's what it says on the axis. So negative 11 kilojoules. Part B asks me to determine if the reaction is exothermic or endothermic. Well, all I have to do is look at my delta H, and because this is a negative value, I know that it must be exothermic. So if delta H is negative, then I have an exothermic reaction. What happens to the temperature in the surroundings? Well, if it's exothermic, the surroundings temperature increases. Surroundings temperature increases if it's an exothermic reaction. And then the last thing is, what's the activation energy? And we want to show work on this. Well, the activation energy is the difference between what I started with, the reactants, and the top part, the top of that bump that we have to go over. That's the energy needed to kickstart the reaction to get us over the hill. So I would do 80 minus 61. And by the way, sometimes we write activation energy as EA. Activation energy can be written a couple different ways, but that's one of the common ways. Activation energy equals 80 minus 61, and that's 19. Again, our units are kilojoules as stated before. Alright, we can look at the next one, our next graph, to determine the enthalpy of formation, or the enthalpy of the reaction, delta H. And again, products minus reactants is how I'll determine that. 30 minus, well, this is about 20, and it looks like these are going up by 10s, 20. No, that's going up by 5, 20, 25, 30. So between 15 and 20, I'm going to call it 18. So I'm going to do 30 minus 18. Of course, that's 12. Is it endothermic or exothermic? Well, it's a positive change. Delta H is positive, so it's endothermic. So what happens to the surroundings temperature? Surroundings temperature decreases because this is an endothermic reaction. And then finally, activation energy. Top minus our lowest point, so I've got 50 minus, and we said our starting point was 18. 50 minus 18, we get 32 kilojoules. Alright, one more problem that I'm going to do, and I think you should have it at that point. Delta H equals the products minus reactants. So we have 0, 5, 10. This looks like 5. So 5 minus, and then I have 10, 15, 20. Okay, that's 15. Products minus reactants. 5 minus 15 is going to be negative 10 kilojoules. Endothermic or exothermic? Well, we have a negative delta H, so it's exothermic. If it's exothermic, the surroundings temperature increases. Oops. And that doesn't fit here, but let's just do this. There we go. And then finally, EA equals the top minus the reactants. So the top is 30 minus reactants were 15. So we had to go up 15 kilojoules to start the reaction. 15 kilojoules is the activation energy.